Wire sizing is a real important element of your system design process. We not only have to choose proper types of wire that will resist the environment that they might be operating in, but we've also got to choose the right size of wire. We're often dealing with electricians or engineers that are used to dealing in the AC world, relatively high voltage world, 110, 220 volts or higher. In photovoltaic systems, we're often dealing with very low voltage systems. 12 volts, 24 volts are typical. Because of the lower voltage, we have higher current. That leads to us needing to choose much larger wires than most other electrical installations are used to. So let's take a few moments to look at some different types of wires that we need to use in photovoltaic systems, and specifically how to size the wire. The two critical regions that we have to deal with are between the solar array and your batteries and controls, and from your batteries and controls onto your load. We can sort of think of the system being broken in half like that. In terms of looking at outdoor wiring, the wiring that goes from module to module or finally from the modules into a field junction box before it's sent a long distance. The type of wire that we need to use is something like this wire, sunlight resistant wire that's specifically been treated and coated with an insulation that's designed to withstand the ultraviolet radiation from the sun. If we don't use the proper type of wire, over years the insulation will crack, become brittle, and break away. And that could lead to increased voltage drop and system failure. Two types of wires that are specifically called out in the U.S. National Electric Code for use in photovoltaic systems are type USE, underground service entrance, and type UF, underground feeder. Both of those are direct burial types of wire. They can withstand very harsh environments. And you should also get these wires sunlight resistant, UV resistant. So once again, this would be the kind of wire that actually connects module junction box to module junction box. You might say to yourself, why do I need sunlight resistant wire if the wire is behind the module? Well, you get reflected light to the back of the modules, and all that ultraviolet light is reflecting onto that wire. So I've seen systems where the module wiring is away from direct exposure to the sun, but if it hasn't been sunlight resistant, it's already starting to crack and peel. So make sure that you choose sunlight resistant wire for any wires that might be exposed to sunlight. There's really two approaches to wire sizing that we use in photovoltaic system design. One is wire sizing based on ampacity, basing the wire size on the maximum current that might be flowing through it. This is typically the technique that's used in standard high voltage AC wiring as well. That's what most electricians are going to be used to. In photovoltaic systems, we don't use that for the majority of our wire sizing problems. We do pay a lot of attention to wire sizing based on ampacity for the connections between our batteries and our inverters. That's the location where the largest amount of current is going to be flowing. Typically, large inverters can draw 100, 200 amps or more. This large amount of current needs to be accommodated by very large wire. Typically a wire that's sized to be at least double-aught, maybe 4-aught wire in American wire gauge standard. Using this size of wire, we can accommodate the normal continuous current flows of 100, 200 or more amps, and also accommodate the surge currents that are even higher than that. This size of wire might be larger than you're typically used to dealing with. Don't think that it's unusual. You should always use extremely large wire for interconnecting your individual batteries and for connecting your batteries to your inverters. The cost involved in using such large wire is actually quite small. You might be concerned that too much expense is going to go into such a large wire, but the typical lengths that are used between the battery bank and an inverter is only a few feet or a few meters. So the total cost of that wire is actually quite small. You should size that wire that ampacity rating should be chosen based on the full continuous power rating of the inverter, not just the particular current that you need today to meet the loads that you've sized your system for. For example, let's say you're sizing an AC system and you have a number of AC loads and you've added up the continuous power draw that it might be. And let's say it's only 2 kilowatts, but you choose a 4 kilowatt inverter and you install that to accommodate future growth. You should size your wire based on the full 4 kilowatts that that inverter could draw, not just the 2 kilowatts that it might draw today. Why? Again, you're building in for future growth, you're accommodating any changes that might occur in the future, and you don't have to rewire your system. Again, the types of sizes of wires that you might be using in this case would be very large wires, at least double-aught or 4-aught cable in American wire gauge standard. The technique that we really want to focus on for photovoltaic system design is not so much wire sizing based on ampacity, but wire sizing based on voltage drop over a distance of wire run. The concern here is that we often have long distances between the array and the batteries and control, and perhaps between the batteries and DC loads. If all of these are operating at relatively low voltages, 12 and 24 volts, we're operating at relatively high currents, and that current flowing through a long distance of wire that's too small would cause too much voltage drop and too much energy loss. We end up using, often, unusually large wires for the connection, especially between the array and the battery. I want to alert you to that fact because when we go through the process of our system calculations, you may end up with wire sizes that are larger than you're used to expecting. Don't be surprised. And in fact, we often encounter resistance by electricians or engineers that are used to dealing with higher voltage AC systems when we propose using large gauge wire for relatively low currents. They go, why? This is wrong. You've made a mistake. We don't need that size wire. And they're wrong. We need larger size wires, not because of ampacity, not because we're carrying the current that that large wire could carry, but because we want the small voltage drop over a long distance that that wire gives to us. Let's take a look graphically at the effect of wire size between a module or a series of modules and batteries and controls. In our diagram, we look at an IV curve first drawn with no wire losses at all. That would be as if we had infinitely large or perfectly sized wires. Now, what we can look at is if we install progressively smaller and smaller diameter, smaller gauge wire between our modules and our battery, the effect is as shown. The IV curve effectively is dragged inwards because we're now introducing resistance. And at a certain current flow, we have a voltage drop. At a higher current flow, we have a higher voltage drop. So the effect is to bring the IV curve in, to slant it inward. Now, so you'd say, well, you're experiencing a voltage drop. But look carefully. If we look at the range of battery voltage that we typically deal with, somewhere around 12 to 14 or so volts, if our battery is operating our modules, let's say at roughly 13 volts or so, we read up from that level to the IV curve and then read across to find that effectively we now have lower current flowing. So the effect of having too small of wire is to reduce the amount of current or the amount of amp hours in a day that would flow. So you could have gone through all of your fancy computer-based sizing to calculate the number of modules you need to deliver your amp hours. And then if in the field you install wires that are too small, you're going to restrict that current flow, and you will not get the amp hours delivered that you predicted in your fancy computer printout. So you can look at your paper and say the system should perform in such a way, but after a few weeks or a few months, the batteries would not have received the charge that they need. They'll progressively go lower and lower in state of charge, and eventually your whole system could fail, simply because the wire between the array and the battery was too small. So this is a primary focus in terms of the installation practice that we go through, size up your array and battery to meet your daily loads, and then size your wires large enough so that you have very little voltage drop, if any at all. We've created for you a summary chart that shows various wire gauges and their associated ampacities and their voltage loss factors, basically their resistance that would lead to voltage drop over distance. For the American wire gauge example, we have all the different gauges of wire, the different sizes, and different ampacities indicated for some different common types of wires. The point here is that choosing the ampacity of the wire is a little bit complex. It depends on the particular situation that that wire finds itself in. Is it in air? Is it in conduit? Is it buried? How many other wires are with it? And so on. Code guidelines give a much more detailed guide as to how to determine the ampacity of wires based on the particular situation and the particular type of insulation that you're using. The associated voltage drop factor that we've indicated is a measurement of resistance of that wire per foot or per meter. These numbers are used for the wire sizing based on voltage drop that I've talked about. We've created for you some guideline charts that allow you to size your wire based on total current that might be flowing and distance between your array and your battery, or your battery and your load. These charts have been designed around a 5% drop or a 2% voltage drop. The 5% drop should be considered really the maximum allowed that you should ever consider between your array and your battery, or your battery and your load. If at all possible, you should size your wires based on only 2% drop. This is economically possible. It doesn't involve choosing wires that's that much more expensive, and it leads to a much more appropriately designed and long-performing system. We can now go through some exercises using these tables and the wire sizing worksheets that we've created to do some examples of looking at current that might be flowing, the distances that that current might have to flow, and choosing the proper size wire to give you only 2% voltage drop. In the system sizing design process, we calculate the number of modules that we need to give us both the current flow and the voltage that we need for that current flow. One of the skills we need is how to wire up these modules in series and parallel connections. What we're going to do in this section is practice, at least on paper, the process of wiring up modules in series and parallel to achieve the current and voltage that we need for our loads. Let's begin with the simplest of systems, a very simple 12-volt array. In this case, we would have 12-volt modules all connected in parallel. Parallel means connecting plus to plus, minus to minus. In this case, the current flow from each module adds together. The voltage of all the modules is the same. In our schematic, we can see that we have individual wires coming from each module plus, coming together to one final wire. The output from each module would flow through its wire, eventually combine together to make one large current flow. This would flow on through our regulator into our battery. The same current would flow back from the battery through one major wire, then would be split up evenly, and the current flow would distribute itself back into each module. This would be an example of simple parallel wiring. What we're looking at is a schematic diagram. Let's take a look at a sort of a more real diagram, a field diagram of what modules might look like connected together in this format. Again, let's look at a simple 12-volt system. All of the modules are lined up together, so all of the pluses are on one side of the array, all of the minuses are on the other. The wire jumps from one plus to another and from one minus to another. The final wire carries all of the current out, and the other wire all of the current back in to the array. In the case of anything greater than 12 volts, 24 volts, 48 volts or greater, we're faced with basically two choices. You could either wire all of your modules together in parallel first to give you the current that you need, and then connect individual 12-volt parallel groups in series to give you the voltage that you need for that current. Or you could connect a string of modules together in series to achieve the voltage that you need, and then connect those series strings together in parallel to give you the current that you need. Electrically, these two methods are equivalent, and we have people designing systems both ways. In actuality, I recommend wiring my systems in series groups that are then connected in parallel. The problem that I see with wiring groups in parallel and then connecting those parallel groups in series is this. In actual field operation, we may have damage or some sort of maintenance work that needs to be done on an array. If you need to remove a parallel group from the circuit in order to work on it, you've removed too much voltage out of your entire array. You're left with an array that doesn't have the full system voltage that you need. The entire array has to be shut down. Whereas if you have series strings wired in parallel and some modules in one string need to be removed or worked on, that string can be removed out of the circuit and you still have other parallel strings operating at full system voltage. So the array is able to continue to charge your batteries and the system is able to continue operating. So in actual field operation, I recommend always wiring systems in series strings that are then connected in parallel. In the case of a 24-volt system, that means we need two modules wired together in series, 12 plus 12 to give 24 nominal volts. Each string at 24 volts is then connected in parallel. The current flowing out of each string flows and combines together into one final wire, flows on through the regulator and into the battery. That same current flows back from the battery through one wire and is split evenly back into current that flows into each parallel string. Again, if we look schematically, we only see sort of a skeleton picture. Let's take a look at a more real-world image of how the modules might be wired up for a 24-volt string. In this case, we actually flip-flop the modules back and forth next to each other. The plus of one module is right next to the minus of another module. We do this because the wiring within the string from the negative of one module to the plus of the next module is quite short. So we basically have groups of two modules making series strings. The pluses of each one of those strings is connected together, and the minuses of each one of those strings is connected together, corresponding to the connections that we made in our schematic drawing. Let's look at one other voltage situation that we typically face in PV systems, and that's 48 volts nominal. If we're dealing with 12-volt modules, that means that we need to make a string of 4 modules connected in series, plus or minus. This gives us one string of 48 volts. If we need more current than one module can deliver, we connect series strings in parallel. If we look at a real-world pictorial of what this might look like, again, for compactness, we have the modules flip-flopped. So a 4-module string at 48 volts involves 4 modules facing in opposite directions. The series interconnections that we need between modules is simply made by a wire going from the negative of one module to the positive of a neighboring module. The final plus wire from one string can combine with the final plus wire of another string. Typically, we find in photovoltaic systems that structures are designed to hold 8 modules. They can be designed to hold more or less, but the 8-module design is a weight and a size that can be lifted by 2 individuals easily. In that case, a 48-volt configuration can only have 2 parallel strings on one structure for 8 modules. You can now take some time to go through the exercise of tracing out the current flow that might occur in a 12-volt, 24-volt, and a 48-volt system. This is useful because I want you to get a feeling for where the current splits, where it comes together, where the voltages are being gained, and where the currents are staying the same and where they're different. So at this time you can work yourself through some exercises that we planned to better understand the wiring schemes of 12 volts, 24 volts, and 48 volts. What I want to pay attention to at this time is how do we go about connecting together the modules, regulators, batteries, loads, all the components that we've talked about in our system design process up to this point. We have some conflicting interests when we start dealing with the details now of how to actually wire up our system. We want maximum reliability, maximize safety, and yet we always want to minimize cost and perhaps minimize complexity. Oftentimes these desirable elements conflict with one another. You can't have everything. So in the process of deciding exactly how we're going to wire up our system and include protection equipment as well, there's always going to be a process of trade-offs, perhaps some slight compromises. We can't compromise too far in any one element. We can't become completely 100% safe. The cost might be astronomical, but we certainly can't be unsafe. We've got to work within certain ranges of choices. What we want to cover during this segment is some of those issues and some of those components that might be involved. When we're dealing with wiring issues, one of the first things that you should always consider and become greater informed about is your local code requirements. In the United States, we have the National Electric Code, which is adopted by most all municipalities as the guiding rules for how systems should be wired. Within the National Electric Code, we have a specific section, Section 690, which is devoted to photovoltaic system wiring. An important consideration that you should keep in the back of your mind when we're dealing with codes is that codes are designed based around strict concern for safety. They are not concerned about cost or efficiencies being compromised by these safety issues. That's to be applauded, but people involved in the business of installing photovoltaic systems might find it difficult to deal with some of these requirements because they add some cost to their system. I think it's important to be able to justify to your final customers any added costs that you're putting in based on safety requirements. Be able to explain to them where those costs come from and why they're justified. In low voltage systems that we're typically dealing with in photovoltaics, 12 and 24 volts, perhaps 48, but 12 and 24 volts are most common. That's an extremely low voltage. Most electricians and inspectors and folks involved in standard electrical practice are used to higher voltage systems. We may be involved in installing components and especially wires that are much larger than they're used to. And I want you to stand firm in your choices for that because, of course, we have to minimize our voltage drop because we have such a low voltage to begin with. Another concern that comes to mind specifically in the United States is UL approval of components. The underwriter's laboratory label on components lends a lot of credibility to the safety of a particular component in your system design. Many inspectors may have to, will look for the UL approval rating, and if you're choosing components that don't have those, you may have to go through a process of explaining to them and giving them more information about the quality of those products. Let's start looking at the different types of parts of our system that we're going to be wiring together. Our concern is how do we wire them and how do we wire it safely. Let's start by looking at battery wiring. Here we might have a system as simple as one module and one battery. That's pretty easy. But in those cases where you have multiple batteries that you have to put together, there's a number of ways that we can wire them. Let's take a look at what some of those configurations might be. If you've got a 12-volt system and you need to have more capacity than one particular battery can give you, you're going to wire your batteries in parallel, plus to plus and minus to minus. The concern here is not to have too many batteries wired in parallel. The consideration is that if we have individual linkages from one plus to the next plus and one minus to the next and so on, that the treatment of all of these batteries wired in parallel might not be equal. You don't want to have some batteries being more charged than others, and so on. The guideline that I like to stick to is having no more than roughly 6 to 8 parallel batteries wired up. If your choices of batteries lead you to having more than 6 to 8 batteries in parallel, I think you should carefully look at choosing a larger battery. If instead of just having an increased capacity, you need to have your battery voltage higher than just a single battery can give you, then you need to connect your batteries in series, plus to minus, plus to minus. Here we show a single string wired in series. If these were 12-volt batteries, this would be an example of a 48-volt single string battery. You may have cases where you need both more voltage than what one battery can give you and more capacity than what one battery can give you. So we would wire up strings of batteries in series to give us the voltage we need, and then connect those strings together in parallel to give us the capacity that we need. A further example is shown with 4 batteries wired in series and 3 of those strings in parallel. Notice that the plus wire is coming in one corner and the minus wire is leaving from the opposite corner. Why are we doing that? That's a simple approach to trying again to equally treat all of our batteries. If we had both of our connections on one string and relied on some sort of parallel connection to link the other strings, we could possibly have a mistreatment of the first connected string compared to the later string. Perhaps there's slight voltage drops in the parallel connection, and the farthest strings away from the initial connecting point might not be charged as much. The strings connected to the connecting points might be charged too much. This would lead to an unequal treating of the battery and loss of life. So by simply bringing in one wire in one corner and tapping out of the battery bank at the opposite corner, I think that's one way to sort of equalize the path that the current would flow through. You can see that if current comes in and flows through the first path, it has to make a couple of connections. To get to the second path, it has to go through one connection and a second connection. And to flow through the third path, it has to go through 2 connections as well. Just a way to try and equalize the treatment of your batteries. If you have a situation of parallel wiring, either multiple strings or like we talked about in our 12-volt situation, and you have a number of batteries to connect in parallel, one advice is instead of using individual wires, to use a continuous strip of copper that's drilled at the right point so that the connecting lugs of the batteries can be connected to the solid copper rod. That would be one of many kind of tricks that you could use to ensure a better system performance in the case of parallel battery strings. One note that we should talk about here, when we're dealing with batteries, we're dealing with danger. Modules are fundamentally safe in the sense that they're current limited. You can short circuit a module safely. It won't run away in current. It won't produce more current than it can handle. But with batteries, you're dealing with an extremely dangerous device. We have to be concerned about short circuits in systems with batteries, drawing tremendous amounts of current, perhaps causing bodily harm or at least dangerous damage, perhaps fires to our equipment. One of the concerns that we can look at is how do we protect our system from short circuits touching right back to our batteries, especially in the case where we have large systems with large amounts of capacity built into our battery bank. An individual battery can deliver thousands of amps per 100 amp hours of battery capacity. This means in systems where we've designed in 1,000 amp hours or more of storage capacity, we could have tens of thousands of amps that could flow from a battery under a short circuit condition. We have to be concerned about protecting our protection. In other words, we have downline from our batteries, perhaps other fuses and circuit breakers. These might not be designed to handle these high levels of short circuit current that might occur under extreme conditions. What we recommend is to install current limiting fuses at the head of each one of our battery strings. These current limiting fuses are specially designed to handle large inrushes of current. However, as in many, many cases when we look at wiring in photovoltaic systems, these fuses are rated and typically designed for the AC world. That's the majority of their usage around the world. We're typically dealing with DC. There's a fundamental difference between AC current treatment of fuses and DC. In the case of AC conditions, multiple or hundreds of times in any second, the current level actually goes to zero. And if we're trying to break a dangerous short circuit current flow, and the current flow actually goes to zero, that's much easier to break, much easier job for a fuse to do. In the case of DC, though, the fuse is handling a continuous current that never goes to zero. Because of this, we have to derate the current breaking capability of these fuses by 90%. So the largest type of fuses that we might use in this case, these current-limiting fuses, would be an example like these, Class RK5 or Class T current-limiting fuses. These fuses are designed to break 200,000 amps of AC current. They can, in other words, they're designed to be able to break up to that much current, AC. Again, consider the fact that when they do that, they'll have an opportunity hundreds of times a second where that current goes to zero, so they can safely break that much current. But in our case of DC systems, we have to derate that current breaking capability, that interrupt rating of that fuse, by 90%. So a 200,000 amp fuse is derated to 20,000 amps. That's plus or minus roughly the amount of DC current that that fuse could safely break. So what we have to think about is how can we break our battery bank into small enough units so that under maybe the worst possible situation, we might have equal or less than 20,000 amps of current flowing from one string. Then we'd install one of these current-limiting fuses to break that much current. Roughly, in terms of general numbers, that size of battery bank might be roughly about 700 amp hours per battery bank. So if you find yourself with your system sizing calculations indicating a larger battery bank than 800 amp hours, you should consider breaking that into individual strings and protecting each one of those strings with a current-limiting fuse. In that way, you're, once again, protecting your protection. You're protecting the downline fuses and circuit breakers that might be in your system. Circuit breakers and fuses are rated for their ability to break current, to stop a dangerous current flow from perhaps catching a wire on fire. Circuit breakers and fuses have basically two kinds of current rating. Most of us are familiar with the first rating, which is the amp rating, the current carrying capability of the circuit breaker or the fuse. For example, these are 30 amp circuit breakers ganged together. That intuitively means that they should allow 30 and maybe a little bit more amps of current to flow under normal circumstances. If the current rises above that rating significantly, the circuit breaker should trip, the fuse should blow. The question is, how much above that rating is the circuit breaker or the fuse designed to operate safely? 100 amps more, 1,000 amps, 10,000, a million amps? There's some realistic upper limit to its safe operation. That's the second rating for circuit breakers and fuses. It's often referred to as the AIC rating, or amps of interrupt current rating, or interrupt rating for a circuit breaker or a fuse. I want to take a moment to look at some examples of both the continuous current flow that's allowed through fuses and circuit breakers, and to examine the interrupt rating of the devices. These are both factors that you should become familiar with when you're choosing your components. We'll notice that the current that's allowed through these safety devices is not simply a go, no-go kind of situation. It depends on time. The amount of current that's allowed to flow through a circuit breaker or a fuse depends on the amount of time. Current at the rating of the device, or slightly higher, is allowed to flow forever. A little bit more current is shut off within a few minutes. A vastly greater amount of current is shut off within a fraction of a second, and so on. Let's take a moment and look at some examples of current ratings over time and interrupt ratings. In all of our photovoltaic systems, we're going to want to install some sort of switching so that we can turn off our electrical power, both from our modules and to our loads and so on. This can be done in two ways. We can either use fused switches, or we could actually use circuit breakers. They both act as overcurrent protection and also can break the current flow. So we can use circuit breakers or fused switches in these various locations in our system. A concern to keep in mind is that all of this switching that we need to be able to do has to be done with DC-rated devices. Don't just grab standard AC products off the supplier's shelf. We have to choose or perhaps even order DC-rated equipment. For example, these circuit breakers are a special order, DC-rated item. In terms of where we locate these disconnect switches or circuit breakers in our system, there should be at least these locations that are covered. We want to disconnect between our array and our charge regulators, and between our charge regulators and our battery. Those two connections should actually be gained together. For example, as shown here, we have actually 3 channels that are physically linked together. The point is that when we throw one switch or one circuit breaker, we're going to want to break the current flowing into the charge regulator from 2 power sources, the array and the battery. So there's 2 points of breaking. Then, depending on our system sophistication, if we have just DC loads, we'll want to have another disconnect point between our battery and our DC loads. And if we have an inverter involved for AC power, we want to disconnect between the battery and the inverter, which is then flowing on to some sort of AC load center. In many cases, you might be dealing with very simple systems. Cost is important. We might have the charge regulator unit act as our central wiring area for a small cabin system where we can simply bring all of the wires into one simple unit that might be mounted on the wall. In a unit like this, we have connection points for both the array wiring, the battery wiring, and some small DC loads, maybe some lights. So the unit itself acts as a central wiring station. It might include, as in this case, array fusing and battery fusing internally, so the safety units are actually built in. But for larger systems, I think you're going to want to consider power centers. Some sort of pre-wired unit that is your central wiring station that includes both connection points, perhaps metering points and charge control points, and your safety, fusing, and disconnect. An example might be this type of power center, where we would have circuit breaker control for incoming current flowing from the array into the system, safety fusing between the array and battery, and between the battery and the loads, and perhaps even circuit breakers for our DC and AC loads. This unit might also include our charge regulation control and metering, as well as generator starting control and so on. I think if you're looking at larger and larger systems, we're now dealing with markets that will accept a more sophisticated approach to central wiring of all of our controls and of our safety protection. Let's look at 2 basic approaches to where all of these disconnects should be put in our system. I think I break things down into 2 classes, a circuit breaker approach and a fused disconnect approach. All systems don't have to be one way or the other. I'm just drawing a distinction to show you an example of how those 2 approaches might be slightly different and still protect our full system. So let's look first at what might be called a circuit breaker method or a circuit breaker approach to disconnecting all of the components. Here what we've drawn is one single box, a physical representation of a box, where all of our wires would be brought together. Let's look at our 2 primary circuits, our charging circuit and our load circuit. The charging circuit involves current flowing from the array to the battery through a charge regulator. In this case, we can see the array plus coming in, going through a circuit breaker, traveling on to our regulator connection. The wire from the regulator, the battery connection, feeds back into the box through another circuit breaker, and that feeds out to the battery plus. Notice that the two circuit breakers are ganged together, so that when one pull is made, both connections are broken, and the regulator is completely isolated from both the array power and the battery power. Let's follow the negative run. From the array negative, power flows into a central negative wiring block. Power flows out to the battery negative. The regulator negative is connected as typically a reference point. Let's look now at the load circuit. In that case, we're not concerned about the array. We have power flowing from the battery plus into a block where we carry the wire across to a circuit breaker that goes to our DC load center. And then we have a return wire coming from the DC load center as a negative, coming into our central negative wiring block, going on to battery negative. There's the current flow to our DC load. If we had an inverter going on to AC loads, we have power coming from the battery, being carried across to a circuit breaker that would go to our inverter plus. Inverter minus, now, we'd return to our box and connect to the battery negative. It's assumed in this diagram that the AC power coming out of the inverter is going to its own dedicated AC distribution box. The small dotted lines that I've included indicate the grounding connections as well. So the array ground, your other boxes that might be involved with holding the regulator, the DC load center, the inverter housing, all of these ground wires come together as well and are all connected at one central point, that negative grounding bar. It's from this point that we send our grounding wire out to our main system ground. It's actually put into the earth. The nice thing about this approach is that all of the components are physically in one box. Be careful to note that the actual sizing of the circuit breakers is going to be quite different. You might have 30 or so amps flowing in your charging circuit breakers, but maybe 200 amps flowing in your inverter circuit breaker, maybe 100 amps flowing in your DC load center breaker. The size of the breakers don't have to be equal at all. So in this approach, we could physically put together circuit breakers of different current carrying capacity. I like that approach. It involves simplicity in terms of wiring, having all of the components physically in one box. An example of that would be a load center like this. Another approach to wiring can involve fused disconnects. Instead of circuit breakers, we're talking about a physical blade type of switch that also has a fuse protection built in. We might look at one example of how that could be wired up. There might be other ways as well, but I think this illustrates the general approach. Again, let's trace out our two circuits that we want to follow, our charging circuit and our load circuit. To follow the charging circuit, we begin with the array plus, which comes in through a fused disconnect switch and travels on to the regulator array connection. From the regulator battery connection, goes back through another fused switch onto our battery plus. The negative connection from the array comes into a central negative wiring, connects to the battery minus. The regulator negative is connected as well as reference. So we've isolated our charging circuit in one fused disconnect box. If we want to look at our load circuitry, I have it drawn in a separate box. I think that would be typically the case, and the reason is because of the differences in current. I think we'll typically have lower currents flowing in our charging circuit, and perhaps very heavy currents flowing, especially if we have inverters, in our load circuit. Physically, it's hard to put a 200 amp fuse and a 30 or 50 amp fuse in the same box. They're just not designed to do that. So you're going to be forced to have at least two separate boxes. Let's look at the load circuit now. We don't need the array considered. We come from battery plus, flowing in through some fused disconnect switches. I show it jumpered so that the power can, in one case, go on to my inverter, and then my inverter negative can come back into a central negative connection point and flow back out to my battery negative. Next to that, I show another fused disconnect that can carry power from my battery to my load center. And the negative from my load center would come into the negative wiring block and flow back out to my battery negative. Again, if I'm choosing large inverters, the inverter fuse might be 100, 150, 200 amp fuse. My load center might involve a 100 amp fuse. The grounding wires are shown, and because we have two separate boxes, we have to actually physically link those together. Then from the system, we can actually run the wire coming in from our array ground, and finally, the grounding wire going out to our system ground. Both of these approaches are fine. Both are used by many installers around the world. I'm simply drawing a distinction between the two so that you can see and perhaps make some choices about component design, sophistication, cost, complexity. All of these issues have to be dealt with on a particular basis. You have to look at your cost, your customer, the possibilities of future growth, and make your choices of components based on that knowledge. A final issue that's real important to cover is system grounding. Typically, we're faced with the situation of having some loads physically separated from our array. It'd be great if we could always have the array right on the roof or right next to our loads. That may not be the case. We may have a separation between our array and its structure and our central wiring system, our batteries and control, and our system ground. In that case, you should make an electrical connection between the structural ground at our array and the system ground for the rest of the system. What this is called is a bonding connection or a bonding wire. We can illustrate it by showing an array some distance from the rest of our system. We should have a local rod sunk at the array, or at the arrays if we have multiple ones, and then a physical wire connected to that ground rod that is connected all the way in to the rod that's used for our main system ground. We're electrically connecting the two rods together. The reason we want to do this is if you have separate ground rods and some sort of lightning strike, let's say, that hit the ground outside. When lightning strikes the ground, it fills the ground with current. There's a tremendous inrush of tens of thousands, if not hundreds of thousands of amps. This current flow through the earth causes a voltage drop in the earth. The earth is not a perfect conductor. There's resistance. And so we have different voltages at different places in what was the ground, what was supposed to be neutrally zero everywhere. We could have tremendous voltage differences, and this could cause electrical currents to be induced and flow and perhaps cause damage to our equipment. By electrically bonding the two ground wires together, if there is a voltage rise in one place, all of the system rises in voltage potential and then settles down. And the probability of problems due to ground currents and induced currents and so on is greatly reduced. By way of summary, we need to consider wiring as carefully as we consider array and battery sizing. We have to look at component characteristics. We have to be sure that we're choosing DC-rated components, not substituting in AC-rated components that may not handle breaking DC currents. We need to understand the current carrying capacity of our switches and fuses so that we can choose the proper rating to allow continuous and perhaps some surge currents to flow through without tripping unnecessarily, and yet choose them large enough and safe enough so that they do protect our system from dangerous short-circuit currents. And finally, we should consider different sort of wiring center approaches that can simplify the wiring for our installers or our users so that their likelihood of making mistakes in this fairly complicated field is minimized. I think by making your choices carefully about wiring components, you can end up with a system that both looks quite good is aesthetically pleasing, is economical, and adds safety to your overall system performance.